Welcome back, everybody. Wonderful to see you all here for the last session of Our Connected Universe. I'm really excited to hear in this session from Ram, an engineer at Spiral Data, all about improving water networks using AIML. Take it away, Ram.
Sorry, I haven't been presenting for a while, so give me a second. Apologies for the delay. Okay, that's better. And just, sorry. Slideshow. Much better. Hi, everyone. Thank you very much for staying on until the last session. I will try to keep it short, but I'll try to make it worthwhile. There were amazing talks all day, so it's a little bit honestly intimidating to talk the last person, but just as a different perspective, this talk will not have a lot of code snippets, but it's more like a zoomed out talk, trying to talk about the problem I personally care a lot about and the problem that my organization, Spiral Data, cares about a lot, and all the aspects of the problem and how Python and its ecosystem is helping us to try to solve that problem. So, and I'm happy to take questions at the end or connect. So just a bit of an outline. We are an Adelaide company based out of the Tonsley precinct. The main thing that we do is big data and machine learning, mainly for water. And we do all the way from consulting, trying to understand the problem, to build, to support. And we are also proud of the AWS award that we got recently. And these are some of our customers. So the main thing is, why do we do what we do, and why do I personally connect with the problem? For those of you who don't know about, UN sets up sustainable development goals for all the world, all the countries as a target, and goal 6 talks about ensuring availability of water and sanitation for all. And this is a mission that we I care deeply personally, because I come from a place where I had to suffer for clean water when I was in childhood, and I had personal experience. But this is not just a developing country's problem. This is a problem that currently exists even in Australia. More than 500,000 Australians, especially in remote Aboriginal communities, do not have access to clean drinking water and sanitation. And just why is that? The problem is extremely complex. Water networks are complex. Everything around water is complex. Just to give you a perspective, in Adelaide, South Australia, most of the people live within the Adelaide metro, but the state is extremely large. The density is around 1 to 2% per kilometer, and so what happens is you have mains that are running for tens of thousands of kilometers, and same is with the sewer main. So this is data just from the SA Water, the biggest utility here, but there are also other utilities who manage especially the sewer main, and it supplies more than 220 billion liters of water. So just the magnitude is so complex, and so is the problems around it. What are the problems? There is a lot of them. I just had to pick few just to keep it short. Aging infrastructure. So most of the pipes that are across Adelaide and most of the cities are over 100 years old, constantly needing monitoring and upgrading. And also the issue with climate change, because there is the encroachment that is coming in that is affecting all the water networks, hurricanes, and also the environment impact, like any leakage from the sewer systems can have like catastrophic effects, especially in very sensitive areas. So we strongly believe most of these problems can be addressed and at least mitigated technologically, but then even technological challenges exist in water networks. The main being technological maturity, because water being an old industry, they're also very resistant to change, and for good reason, because they are transferring water which is being ingested by us, so any mistakes can be catastrophic. And also the other problem is siloed solutions. So most of the solutions that they build are specific for those use cases and cannot be leveraged across multiple So and with that comes the issue with data, because every vendor has their own data standards, data provenance, data management. But then it's not all dull and gloomy. There are also a lot of opportunities. The biggest that, in my opinion, is the collaboration. Water industry is very highly collaborative. Utilities talk to each other constantly, sharing technological advantages. And there is also a growing sensor fleet of IoT 4 devices that is exponentially increasing. But then the last part of the puzzle is, how do you use this data? How do you use this data to solve problems that are important for them, to make it a lot more easier for the water utilities to maintain the infrastructure and also to meet up with the existing demand? So the question is, do we have a silver bullet? No, we don't. And the idea is, can we at least design a framework? But the framework is not just technological. The framework includes people who are going to build this, people who are going to use this, the data that needs to be part of this, the tools that is going to be part of it. And we are just going to tell about the framework that we come about, mainly on how do we leverage all these pillars of data, people, platform, and process, and especially using AI, machine learning, to create what we call as decision advantages. Decisions around operational improvements, decision around strategic investments. Like, for example, the talk in the morning in Hall C talked about the pipes monitoring using geospatial data. Things like, we don't use geospatial, but it is a big deal because it involves hundreds of millions of dollars to do any upgrades. And so and you need to do that by maximizing value, by reducing cost, effort, and time. And what we see is Python has a role to play in every part of that. Python helps us to handle data better, disparate data better. It helps us to streamline the process of development. It helps us to integrate platforms, and it also helps us to communicate better with people using dashboards, UIs, everything. So I'll just give a brief outline of how we go through the process. So the main challenge here is, as I said, the technological maturity is very low in water utilities, and as a result, people don't know what they want until they see it. So the idea is, how do we rapidly build solutions that the customers can have a look and feel and use it before they say, yes, this is what we want, this is something we don't want. And the idea is there are multiple stakeholders here, the customers who are going to use it, people who are going to pay for it, people who are building it and testing it. And the idea, and what we see is Python provides a framework, especially the REPL framework, that helps us to prototype it rapidly, share with the customers using Streamlit, and once it is iterated, we also use like UI UX using Bokeh, HoloViz, and also APIs using Fast API. So these are a lot of them are big ones, but especially I wanted to call out the small people, like the packages that are being maintained by one person, two person, especially like JupyText. JupyText is a godsend because data scientists love the REPL framework, they want the notebooks, but software engineers don't want to touch it with a 10-foot pole. So the idea is JupyText helps us to use light percent formats where the data scientists are happy and go on to do the job, but the software engineers are also happy because now it's plain text files. You can lint it, you can test it, you can do code reviews on it, and you can do source control on it. So, yeah, I mean, the environment is so rich that it helps to solve a lot of the problems. So this is the platform that we, at a very schematic level, again, there is data, mainly the sensor data that comes in, and then there is a whole heap of data engineering that happens, and then there is the platform itself, with the core is building machine learning models, wrapped in DevOps and security, and then the output gets through the alerts, analytics, and API gateways. So just to give a context regarding the challenges in data engineering, data can come in any form. Some utilities are very advanced and they have like extremely good data provenance and data management. Some utilities, they just have flat files that they copy it into a hard drive and ship it to you. And similarly, the data velocity is also quite different. There are sensors that can stream up to like hundreds of hertz that needs to be captured and maintained. And then the extraction patterns are also complex, sometimes real, sometimes batch. And the volume is also sometimes massive. Again, there is a lot of the tools that we have to use in order to integrate them across different use cases, different customers. Again, like you see the richness of the the Python ecosystem that is helping us to leverage this. Like we use all SQL Alchemy is a godsend because we can use that across all kinds of databases, and also similarly fast API. And especially I wanted to call out the Python wrapper that is being maintained by Sergey. Z-Standard, the core implementation is by Meta for Facebook, but then there are Python wrappers that are being maintained by single developers who are just doing it for passion, and that helps us to compress data at a massive scale and being able to solve these problems. So the core of our work is AML Workbench. The plenary talk talked a lot about AI bias. The other aspect of the AI is the accuracy and the reliability, especially in critical infrastructures like water. Because if you build an AI model that gives unphysical results like negative pressure, the customer is never going to talk to us again. So the idea is, how do you build reliable machine learning models but the speed to value needs to be high, but then the other important challenge is most of the utilities are extremely busy. They have very little time, and then you need to make, like whatever little time you have, you need to utilize it. Again, the way we are trying to see is a lot of our work is built on anomaly detection, and what we try to do is we try to use unsupervised model against stat model sklearn to build a labeling pipeline. Again, it's based on Python Label Studio, and SMEs gives us feedback on how to, what kind of data is an actual anomaly, what is not an anomaly, and then we use that to again build supervised models. And then again, we have model registries using MLflow, and then once the model, and this gets iterated, it's not a single process, right? We constantly iterate this a lot of times until the customers are satisfied with the reliability before it can get deployed. Again, like one of the amazing tools that is just maintained by a single person is Pyode, which is an anomaly detecting package, and anybody who's working on anomaly detection, I strongly encourage to take a look at that. So I talked a lot about the problems. I talked a lot about in terms of abstract of how Python is using. We just wanted to give a couple of real-world examples. So this is a real-world example. This was a massive pipe break a few years back in King William Street, just down across the road. So this is caused by what the engineers call as pressure transience. So there is constant flow of water happening through the network that is at a certain pressure. But then if there is a sudden increase in demand, like say during halftime of the Matildas game, if everybody went to the restroom, there is going to be a sudden spike in demand that is going to, what happens is it creates like a hammer effect. You are hitting the network with a hammer at a very high velocity and very high force. The technical term is pressure transience. And these are these happen across the network, but the understanding is there is very little analytics around this. Where does it happen? When does it happen? How strong is the impact? And what is the likely impact on that? So just to give a schematics of how this works, so the transients are being generated, and this hammer effect that keeps ongoing, it's not one time, it keeps happening continuously, and that creates what, again, in mechanical terms is fatigue. And then fatigue is like similar to human fatigue, which leads to burnout, but here it leads to breaks and cracks. So if it cracks, it's not just a challenge of fixing it. There is not just an operational cost. There is also a huge capital cost invested in replacing, and more importantly, there is a large downstream effect of this affects water quality for a long time, few days, because there is there is I would say, the unnecessary sediments that coming into the network that cannot be cleaned easily, and that affects a lot of things, especially vulnerable population if they need access to clean water. This is a major issue. And so the first thing is, detecting it requires sensors at really high frequencies. So the sensors that we worked on this with SA Water, what they deployed is over 100 hertz, and that roughly translates to a few billion records per sensor per year. It's not manually possible to analyze any of them, so the first kind of models that we built is trying to extract patterns from these data that are equivalent to the pressure transient. There is also a lot of noise in this, and then but what they want is a specific pattern where there is a sudden increase or a decrease, and then there is a flattening out. We were able to design these algorithms. The main criteria for them was the reliability, because without that, nothing moves forward. But then the other thing is also the solution needs to be fast, because they need real-time monitoring. Because if there is an impending break, they need to be proactive rather than being reactive. And the other thing is also scalable. You can do it for one sensor, but then the idea is, can you do it for 100 sensors? What happened is we were able to extract it, but it's still more than 100 events per week per sensor. And that's still not possible for any humans to do it, just because they are maxed out. They do it, they have minimal time, and then they still can't analyze each and every event independently. And so the next step was we wanted to group them automatically. Again, we used a lot of the information within the characteristics of time series using various metrics, dynamic time warping, and all the other things. But also we worked with SMEs to understand the type of transients. Like, for example, what's the transient that is going to be created by a fire testing versus a large custom, like a large plant, for example, or like a large high-rise apartments, because that was important for them to figure out what's the source. And then again, needs to be reliable. Yes, it significantly improved. Now they only had to analyze a few tens of groups. But the challenge is this is one sensor. What happens if there are 100 sensors or 1,000 sensors? What we did was we started to build analytics around it, and then like across all the groups, we tried to look for patterns on daytime, and then what we were able to surface those anomalies. And one of them is shown here, which is like the same kind of pattern happens every Friday in the morning. And these are the information that is useful for them, because now they can go and do field testing, and then they came back and said, yes, this was a fire testing that was happening, especially in peak demand times. And I think they are working with them to try to move the testing time so that it doesn't affect the infrastructure. And similarly, there were other work that we did in trying to understand, is that the characteristics change over time? Is there new transient behavior that is coming in, that is stopping? And so the idea is, this is what we call as decision advantage. How do you take the raw data and then try to create as much insights as possible automatically for them that are reliable and accurate, that they can act upon and create some kind of a value? And so the second one I wanted to talk about is Alexandrina Council. Alexandrina is just 50 kilometers down south. For those of you who are new in Adelaide, I strongly recommend going there, because it's where the River Murray meets the sea, and it's a beautiful place. The challenge is it's a large geography. The council is over 1,000 square kilometers. It's very ecologically sensitive. There are few people, but then there are even fewer employees. And maintaining the wastewater network is really hard for such a large geography with such few people. Excuse me. And the challenge is, the drains can get blocked. There are a lot of reasons that it can get blocked. The predominant one being the trees' roots trying to force its way into the sewer network. And what this happens is, if there is a block, there is a back pressure happening, and then this can cause spills, and then spills, especially around the delta of the Murray River, has a strong environmental impact. The challenge is there are no alerts that are present at this time, because most of the alerts in the Modbus system to control these pumps is based on just thresholds. Has it reached the start limit, or has it reached the stop limit? And so since there are no alerts, they have these issues happening from time to time. And so we are working with them to create a solution that is of operational value to them. So the data then again we worked with is for over 5 areas, and then they had 54 pump stations and over 800 million samples. So the idea here is, so this is what they call as, there are multiple pump stations, and then there are sumps that are associated with them. So there is sewer water coming in from every residential or other commercial buildings, and then it gets into the main network, which then goes to the pump station. It gets pumped all the way to the wastewater treatment plant. And so what happens is, as you can see, the red there, it's slowly racing, but then it's not below the lower limit to raise an alarm, and it is not above the higher limit to raise an alarm. So unless somebody sees this data manually, constantly inspecting the dashboards, there's no way for them to know. And likewise, in this specific scenario, they had no idea about this, and it caused a spill where state government had to get involved and federal government got to get involved. And there are a lot of other cascading issues as well. It affects tourism, the main source of economy, and a lot of things. So what we were trying to do is, can we find patterns that can prevent these large blockages to get spilled? So there, and as you can see from the data, the red circle shows there was a small block that happened that got released for short period of time, and then the larger block ensued. So we were able to pick up this from the historical study. So ideally, if a solution was in place, an alert would have gone out when the small block happened and released, and then the field investigators could have taken a look, solved the block before the environmental impact happened. So there are a lot of problems in water networks, and what I'm trying to do is just give you a flavor of some of the very, very small, tiny piece of the problems that we are trying to solve. And Python is helping us to solve from all sides. Like, it is helping us to better communicate with the customers, build these solutions faster, deploy them better, and also maintain them better. So, summary, if there are just 3 things that I would like people to remember, it's just that machine learning has a huge potential to improving water network utilities, especially automatically analyzing data, identifying patterns, and creating alerts, and helps them to do better decisions. And Python is the base for all of the technology to be made possible. But more importantly, that a lot more people with the right skill sets needs to be involved in solving these problems. A lot of people are involved in energy transition towards net zero, but then we also need a lot more people to be involved in solving water problems. As Gibson said, the future is here. It's just not evenly distributed, especially not for the water networks. So, yeah, if you want to learn more about us, I'm here in PyCon till Sunday, or you can go online. We also have a newsletter where we just don't talk about our work, but we talk about the tech in general across the water networks. And yeah, I mean, feel free to email us, and we are looking for good people who are motivated to make a difference to solving socially important problems. People who are happy to work with ambiguity, but even in general, if you want to know more about the area. So, thank you.
Thank you, Ram. That was a fascinating session. We may have time for 1 or 2 questions if anyone in the audience would like to ask a question. I think I can see a hand. Yes, excellent. We have a question.
That was a really interesting talk. Personally, I work in a similar space where I'm delivering AI and ML-based solutions to sort of legacy or very traditional industries, and I have a lot of trouble building confidence with those customers, especially when you're sort of the first pass at bringing information systems in and you're bringing in AI stuff. I'd be interested to know how your experience has been building confidence in systems like this, especially hands-off automated ones.
Yes, it is a challenge. It is an ongoing challenge. But what we realized is there are a lot more they're open to hearing ideas that are not operational. So if you go and tell them that we can help you to make strategic decisions of analyzing historical data to say, like, well, this part of your asset is bad, needs more maintenance, they're all ears. But if you want to do any modifications to their operational, day-to-day operations in terms of maintaining, then they are a lot more resistant. So the idea is you try to get in and start communicating with them at a more strategic level and trying to solve those problems first and then slowly get into the operational. I mean, that's been what our experience has been.
I can't see all your wonderful faces through the lighting. So is there a second question in the audience? I feel like an auctioneer going twice. No, there isn't. Ram, thank you very much for a fantastic session. Here is a small gift to say thank you for your talk.
Thank you very much.
Chris, would you like to come down and join me? We won't do an extended track close, but from myself and from Chris, we wanted to say thank you very much for coming and joining us at the Our Connected Universe track. It's the first time we've run this track together, and we're delighted that you could all be here. Thank you.